If you recall, when we first introduced logarithm, I mentioned that logarithm was defined to help solve for the exponents. Therefore, we can solve simple equations simply by recognizing these two expressions, although one exponential, one logarithmic, have the equivalent mathematical meanings. Let's solve these simple equations by rewriting the equivalent exponential or logarithmic expression. For this first equation, just like any other equation, we want to simplify it as much as possible. Therefore, the very first step is to divide this equation, both sides, by 7. Therefore, left-hand side, we have 3 to the power of 6 minus x. Right-hand side, 9. And as you can see, our unknown x, which is what we need to solve for, appears on the exponent. Therefore, we need to rewrite this exponential expression into its equivalent logarithmic expression. When you do the rewrite, it's really simple. You keep the base, so you have log base of 3, and then you switch the place of the other two parameters. So now you have log base 3 of 9 equals to 6 minus x. And you can either use a calculator, but really you don't need to evaluate log base 3 of 9. Since 3 to the second power is 9, therefore log base 3 of 9 equals to 2. Therefore, 6 minus x equals to 2. From here, we can easily solve for x to be 4. For this equation, again, we want to simplify it as much as possible. So we subtract both sides by 1. And then we divide both sides by 2. And then we want to rewrite this logarithmic expression into its equivalent exponential expression so that we can solve for x. And we know that natural logarithm has an implied base of e, the natural base constant. Therefore, when rewritten into the exponential form, it is e, the same base, to the first power equals to 2x minus 3. And we know that e to the first power is approximately 2.718. From here, we can solve for x to be approximately 2.859. For problem C, again, simplify this equation by subtracting both sides by 2 and rewrite this, again, logarithmic expression into the exponential expression. So we keep the same base 0.3 to the second power equals to x. Therefore, that simply equals to 0.09. Lastly, for this equation, it is given in the exponential expression. We want to rewrite it into its equivalent logarithmic expression. And here we have a base of e. Therefore, we rewrite it into the natural logarithm expression. ln e, which is the logarithm with a base of e, equals to x squared minus x. And we can use the calculator to find out that ln2 is approximately 0.6931. We rearrange this equation, and as you can see, this is a quadratic equation. In this case, it's difficult to factorize it, but we can always use the quadratic formula, substitute in all the coefficients, and we get 2 approximate solutions for x. If you remember, both exponential function and logarithmic function are one-to-one functions, which means that on their graph, they pass not only the vertical line test as well as the horizontal line test. Or in other words, for every independent variable value, there could be exactly one corresponding dependent variable value. So algebraically, it means that for a to the power of x1 equals to a to the power of x2. This is true if and only if x1 equals to x2. Similarly, we can write the one-to-one property for logarithmic functions, that log base a of x1 equals to log base a of x2. This is true if and only if x1 equals to x2. And we can apply the one-to-one property to solve equations. However, you have to be cautious. You can only apply one-to-one property if the two expressions have the same base. So let's apply the one-to-one property to solve these two equations. Notice that there's a similarity between these two equations. Think about it when you follow the video. Let's look at this equation. On the left-hand side, we have e to the power of x squared minus 2. On the right-hand side, we have e to the power of 2x plus 1. Since we have both exponential expressions and they have the same base, therefore we can apply one-to-one property, which states that if these two are the same, then their exponents must be the same. Therefore, we have x squared minus 2 equals to 2x plus 1. Rearrange it. We got this, again, quadratic equation, not difficult to solve. We can factorize it, but even if you cannot, you can always use the quadratic formula. And from here, we can solve for x to be either 3 or negative 1. And they are both solutions to this equation. Now let's look at this equation. On the left-hand side, we have the common logarithm of x squared minus 2. On the right-hand side, we have the common logarithm of 2x plus 1. And we know that common logarithm has the implied base of 10. So again, we have the same base on both sides of this equation. So again, we can apply the one-to-one property. We can rewrite the equation into x squared minus 2 equals to 2x plus 1. At this point, you might have already realized that this looks exactly the same as the previous problem. And we can rearrange it into the same quadratic form. We can factorize it in the same way and get the same solutions. So problem solved. Well, is it really? Did you notice anything that might have been wrong with this solution? I want you to substitute these back into the original equation to see if the original equation is satisfied. And you might notice that if you substitute x2 equals to negative 1 into the original equation, you will have log negative 1 on both sides, which is undefined. Therefore, this is not the solution to the equation. Therefore, this equation has only one solution, which is x equals to 3. There's a difference between exponential functions and logarithmic function. If you remember, for exponential functions, the domain is all real number. For logarithmic function, however, the domain only includes when x is positive. We've learned about the important properties of logarithms, the product property, quotient property, and the power property, and some equations must be solved using these properties. Let's look at these equations one by one. For this equation, we do have both exponential expressions on both sides of this equation, but they do not have the same base. Therefore, you shouldn't equate x to be x minus 2. That will be incorrect. To solve this equation, I will still first use the one-to-one property, but reversely. I'm going to take the logarithm of both sides of this equation. I can choose any base I want, but for convenience, I'm going to choose the base of 10, the common logarithm. So, since 3 to the power of x equals to 7 to the power of x minus 2, then if I take common logarithm of both sides, I get this equation. Then I can apply the power property of logarithm. I can pull out the exponent as a coefficient in front of the logarithm. So for the left-hand side, I have x multiplied by log 3. On the right-hand side, I have x minus 2 multiplied by log 7. So I can rearrange this equation and get x divided by x minus 2 equals to common logarithm log 7 over log 3. And I can evaluate this right-hand side to be approximately 1.771. So now I have a very simple equation, x over x minus 2 equals to 1.771. I can solve x from this equation to be approximately 4.593. Let's look at this equation. One of the very common mistakes will be for a student to rewrite this equation into the form x plus 2 equals to x plus 6, simply by getting rid of the logarithm sign. This is when a student thinks he or she is applying the one-to-one property. However, if you do understand the one-to-one property, you would know that this approach is completely incorrect. So please do not make this mistake. Instead, we need to first apply the product property to condense the left-hand side into this form. And now, on both sides of this equation, we have single logarithmic expression with the same base of 2. And now we can apply the 1-to-1 property to get x multiplied by x plus 2 equals to x plus 6. This can be expanded and rearranged into a quadratic equation that we are very familiar with, and we can solve for 2 solutions from the quadratic equation. However, when you're working with logarithm, you still have to be very careful. If you substitute these 2 solutions back into your original equation, you will realize that x equals to -3 cannot be a solution. Therefore, the only solution for this problem is x equals to 2. For this equation, first we want to use the properties of logarithm to condense the left-hand side into one single logarithmic expression. So we use not only the power property but also the quotient property to rewrite the equation into this form. And now we can rewrite this logarithmic expression into its equivalent exponential expression and get this rational equation. And to solve this rational equation, we multiply both sides by x minus 1. But be careful, you want to make a note that x cannot be 1 because originally the denominator cannot be 0. And now, rearrange this, we get a quadratic equation. From here, we can solve for x to be 2. And you want to double check to see if this solution will satisfy the original equation, and it is a valid solution. Now I'm going to show how to solve these 2 equations by recognizing that they both have a quadratic form. To solve this kind of equation, it is crucially important that you are familiar with the exponential property, that you know that e to the power of 2x equals to e to the power of x, and then raised to the second power. Therefore, you can rewrite this equation into this form, which should look very familiar to you, because it has a similar quadratic equation form. If you want to, you can rewrite this into u squared minus 3u minus 4 equals to 0. Just in this case, e to the x power is u. So you can solve this equation just like you solve a quadratic equation by either factorizing it, or you can always rely on the quadratic formula. In this case, it is not very difficult to factorize. So we have this. And from here, we can solve for e to the x power to be either 4 or -1. But your job is not done here, because it is your purpose to solve for the unknown x. Therefore, you need to continue on. From the first equation, we can rewrite this into its equivalent natural logarithm form and solve for x to be approximately 1.386. For the second equation, you will realize that it is impossible for e to the x power to be -1. Therefore, that would not yield any solution for you. So the only solution in this case is x equals to 1.386. For this equation, similarly, you can solve this by recognizing that 4 equals to 2 to the second power. Therefore, you can rewrite this equation into 2 to the x power to the second power minus 2 to the x power minus 6 equals to 0. Again, this should be a very familiar quadratic form to you. If you want to, you can rewrite this into u squared minus u minus 6 equals to 0. In this case, u is 2 to the power of x. So you can again factorize this quadratic equation and then solve for 2 to the power of x to be either 3 or -2. Again, your job is not done. From the first equation, rewrite this into the logarithmic form and solve for x to be approximately 1.585. The second equation is impossible. It will not yield any solution. Therefore, the only valid solution in this equation is 1.585.